You'll recall that when we were talking about functions, we said if a function had two inputs and two outputs, or really the same number of inputs, the same number of outputs, that was a transformation. If there are two inputs and two outputs, we could call it a transformation of the plane. A function like that would have to have two inputs, let's maybe call them x and y, and then the output would consist of two numbers too. We could represent it as a vector. So the first output, maybe it will be some function of the two inputs, and the second output will be another function of the two inputs. So we could think, well, my u coordinate of the output is some function of x and y, and the v coordinate of the output is some other function of x and y. So every point over here, that function f turns into another point over here. So each point in xy space is transformed to another point in uv space through these two functions of two variables, or you could think of it as a single function, this transformation function f. So if we have now a region in the xy plane, we might ask, with our transformation, what new region does that get turned into? So another question we might ask is, well, if we have a tiny box over here in the original xy space, what size will that box become under the transformation? So it will probably be transformed into a different region, right? And our question will be, well, how much did an individual box get stretched via this transformation? That's going to be important when we're doing integrals, because we're going to be very interested in tiny boxes and how does a tiny box in one location transform to a tiny region in the other location. In particular, what's the stretching factor that does that? Now, you're actually pretty familiar with one transformation, the polar coordinate transformation. You can see that you have an x value and a y value, right? Both are functions of r and theta. So that can be written as a function of two inputs with two outputs. So the two inputs are the radius and the angle theta, and the two outputs are the x and y, right? The first output, r cosine theta, that's x, and the second output, r sine theta, is y. So here's an example of a region in r theta space. This is the region where r goes from 0 to 2, and theta goes from 0 to 2 pi. So this is pretty easy to represent in coordinates, right, or in inequalities. R is going from 0 to 2. Theta is going from 0 to 2 pi. So what region does that get transformed to under this transformation, right? Every r theta point here is going to be transformed to a new point. Well, if theta is the direction, if we interpret theta as the direction that we face in xy space, and r is the distance we walk out, we're always walking out a distance somewhere between 0 and 2, no matter what direction we face, and we're turning all the way around. So this must specify this entire circle of radius 2 here in xy space. So every point here gets transformed by those two equations, or by this single function with two inputs and two outputs, gets transformed to another point over here in this space. A good question would be, well, if we have a tiny rectangle over here, what is that going to be transformed into over here? Some kind of keystone shape. And what will the stretching factor be? So, okay, well, let's look at another example. We have a transformation. U is y minus x, and v is y plus x over 2. And we want to transform a particular parallelogram that we have in xy space. So I want to figure out, first question will be, well, what does that parallelogram turn into when we have this particular transformation? Let's draw the parallelogram first. The first equation says that y equals x, so that's one boundary of our parallelogram, just the line y equals x. And the other one says y equals x plus 3. So that would be, let's see, go up 1, 2, 3, and now y equals x plus 3. And then we have this bound. It's a line with slope 1/2 and intercept, slope negative 1/2 and intercept 3. So this line's going out this way. And the other one we have, it's the same slope, but it's got intercept 6. So go up an extra 3 here, up to 6, and draw a line with the same slope. up to my ability to draw straight lines, we're talking about this parallelogram here in the xy plane. And our question is, if we have equations that turn x and y into two numbers u and v, right? We have a function with two inputs x and y and two outputs u and v, then what does that region transform to? Well, the key to doing this is to transform the boundaries. Let's transform this first boundary, y equals x. Now, if we go up and look, if we have this equation where y equals x, then we can plug that into this this curve here. Let's see, and we get, well, if y is equal to x, then y minus x is x minus x, so we get the curve u equals 0. So this line here, y equals x, actually turns into a vertical line where u is equal to 0. So that's one boundary. We're just going to transform all four boundaries, and that will tell us what the region is. On this next one, y minus x is equal to, y minus x would be equal to 3, right? So that would mean, since u is y minus x, u is being transformed to the line u equal 3. 1, 2, 3. Okay. That transforms our other boundary curve. So that was, let's see, that was this line here, right? Y equals x plus 3. That came over and became this vertical line here, u equal 3. Alright, next one. If y is equal to negative x plus 2, I notice that if I add x plus 2 to both sides, I get y equals, or y plus x over 2 is 3. But then looking at my transformation, v is equal to y plus x over 2, so this must be the curve where v is 3. So count up 1, 2, 3, and we get this line here. Also, this last boundary, if I do the same thing, y plus x over 2 is equal to 6. So that says that v is equal to 6. 1, 2, 3. Okay. So this region would be kind of hard to describe with a set of inequalities, because whether you try to put it between two vertical lines like this or between two horizontal lines, the character of the function changes as you move across it or as you move up through it. So this region you'd have to actually break into three regions, right? Y between these two constants, then then the x's go between these two bounds. For y between these two constants, the x go between these two bounds, and for y between these two constants, x can go between these two bounds. So that's going to require three sets of two inequalities each to describe each of these three different regions within this area. But here we have a nice rectangle, and the description is very simple. U is just between 0 and 3, and V is between 3 and 6. So very, very easily described region in this case. Let's look at another example. Okay, here we have a transformation. U is equal to x, and v is equal to x times y. So both u and v are functions of, well, we could say x and y. It's just u doesn't depend so much on y. So this is a transformation, two inputs x and y and two outputs u and v. So this is going to turn the xy plane into the uv plane somehow. Let's look at the region in the xy plane. The x is between 1 and 2. So if this is 1 and that's 2, x has got to be in that region there. Okay, between 1 and 2. And y is between 1 over x and 2 over x. Now if I draw the graph of 1 over x, 1 over 1 is 1, and 1 over 2 is 1/2, so we have a curve that's kind of coming down like this. It's got a vertical asymptote at 0. Y equals 2 over x also has a vertical asymptote at 0, but at 1, this one has a value of 2, and at 2 it has a value of 1. So we have kind of an interesting shape here. Looks something like this. Okay. And our question is, what will that shape transform to in when we apply this transformation that u is equal to x and v is equal to x times y. We'll just transform each of the boundary curves. When x equals 1, well, u is x, so that tells us u equals 1 no matter what v is. So over here in u space we have this line u equal 1. Okay, and when x equals 2, that's our other boundary curve, u is also equal to 2, so again we have a vertical line u equal to 2 over here in uv space. Now let's see, when y is 1 over x, notice that x times y will be 1. That tells me that v equals 1. So this line, y equals 1 over x, became this line, v equals 1. And when y is equal to 2 over x, x times y will be equal to 2, but of course x times y is v, so we'll get v equal to 2. Well, this transformation turned this region, which was maybe a little bit messy, into a nice square region, like that. So a lot of times we can use transformations to take a messy region and make it nicer for us.